Welcome everybody, my name is Andrea Maioli and I am a PhD student at Politecnico di Milano in Italy. Our work consists in a set of analysis and testing technique for identifying and evaluating unexpected behaviors that affect the battery-less devices of the Internet of Things. The devices of the Internet of Things are powered only using batteries, which must be periodically recharged, replaced, and disposed. This introduces a significant environmental impact, and to overcome this problem, researchers want to replace batteries with energy harvesting technologies. Here, a device is powered only using the energy harvested from the environment, which is then stored inside a capacitor that acts as an energy buffer. Unfortunately, using such constrained energy source causes devices to compute intermittently. So the device is initially powered off and harvests energy to recharge its capacitor. When it has sufficient energy, it powers on and starts computing until it empties its energy buffer. Here the device immediately shuts down and loses all the computational state. Note that this happens because these devices are resource constrained and do not have an operating system that manages this kind of situation. This clearly harms program forward progress, as in the next power cycle, the device will have to restart the computation all over again. To overcome this problem, the literature provides various techniques that are all based on the same idea. During the computation, the device pauses the program execution and saves a copy of its volatile state onto a non-volatile memory location, which is persistent across power failures. This copy, called checkpoint, includes the program counter, the stack pointer, the register file, and the main memory. Then, when the device has enough energy to restart the computation, it restores the checkpoint and the computation resumes from where it stopped. However, checkpoint operation introduce a computational and energy overhead which are proportional to the dimension of the saved state. To reduce such overhead, mixed volatile systems directly allocate portions of the main memory onto a non-volatile memory location, which is internal to the microcontroller unit. Unfortunately, this may cause an unexpected behavior which is partially recognized as intermittent anomaly. So let us consider the execution of this program where variable a is non-volatile. We set a equal to 0 and then we save a checkpoint, which does not include a since it is already non-volatile. Now we basically increment a by 1, so we set b equal to 0, which is the value of a, we increment b to 1, and we update a to 1. Now a power failure happens. When the device has enough energy to restart the computation, we restore the checkpoint but not a, since it is non-volatile, and the computation resumes from line 2. This is where the intermittent anomaly happens. In fact, line 2 reads a value of a that a future operation, that is line 4, produced during the previous power cycle. As a consequence, b is now set to 1 instead of 0. We increment b to 2, and we set a equal to 2. This result differs from the one of an equivalent continuous execution of this same program. However, the problem is that the literature analyzes only the described instance of intermittent anomalies, but that can also happen in other scenarios. For example, when we allocate the stack or the heap segments onto non-volatile memory, or when a program interacts with the environment. Moreover, the literature does not provide a general technique to test the intermittent executions of a program, and we cannot use the techniques for testing a continuous execution of a program as they are not conceived for testing intermittent executions and they do not account for power failures. For instance, exhaustively testing intermittent executions is a non-trivial operation. In general, a checkpoint can be triggered at any point during the program execution. So, to execute an exhaustive test, we need to test a checkpoint before each single instruction. Then, power failures are unpredictable and can happen at any instant. So, for each one of these checkpoints, we need to simulate a power failure after each instruction. This generates all the possible combinations of checkpoint and power failures that we need to test. Finally, we need to verify that the computed results match the ones of a continuous execution, and for doing so, after each power failure, we need to compare the runtime state with the one of an equivalent continuous execution. This means that if a program executes n machine code instructions in a continuous execution, to exhaustively test its intermittent executions, we need to execute n to the power of 3 machine code instructions and to perform n to the power of 2 state comparisons. To put things into perspective, the simplest benchmark used in this domain is CRC, for which a continuous execution runs 50,000 machine code instructions. Testing all the possible intermittent execution of CRC requires us to execute 10 to the power of 13 machine code instructions and to perform 10 to the power of 9 state comparisons. This clearly makes hardware-based testing not practical, and also software-based testing needs some improvements, as in fact such high number of state comparisons limits the number of machine code instructions that we are able to execute per second. For instance, our simulation environment is able to execute 50,000 instructions per second on modern hardware. That means that to test all the possible intermittent execution of CRC, we need 14 years. So, to overcome these problems, we first classify and analyze intermittent anomalies in scenarios that current literature overlooks. Then, we design a set of techniques for testing intermittent executions in practical time, and finally we implement our techniques into a tool, which we call Sheptic, and we evaluate its performance. The intermittence anomaly which we described before can happen whenever there is a memory location that is allocated onto non-volatile memory, and can cause unexpected results. We call this anomaly data access anomaly. A data access anomaly happens because there is an instruction, which we call producer, which alters a non-volatile memory location. Then, a power failure causes the re-execution of another instruction, which we call consumer, that reads the altered non-volatile memory state. So this consumer-producer idea allows us to state that a data access anomaly can happen only when the program has a sequence of instructions such that the first one is a consumer, the last one is a producer, they both target the same non-volatile memory location, and no checkpoint happens inside this sequence. So note that for presentation purposes, we show this analysis at a source code level, whether instead in our analysis we focus on machine code instructions. Moreover, we identify other instances of intermittence anomalies that follows this same pattern, which applies to any memory-based anomaly. Following such pattern, we identify that when we allocate the stack onto non-volatile memory, we may have an activation record anomaly that invalidates the activation record of functions. For example, let us consider the execution of this program where the stack is allocated onto non-volatile memory. We execute a call to function f1, which allocates a stack frame for f1 and writes f1 activation record inside it. Note that the activation record contains f1 return address, which points to line 7. Then we enter the function and we save a checkpoint, which does not include the stack since it is already non-volatile. We continue the execution and we execute a return instruction. So we pop f1 return address from the stack and we deallocate the f1 frame. Now, as the popped address points to line 7, we execute a call to function f2, which, as we previously described, allocates f2 stack frame and writes f2 activation record inside it. Note that, as we previously deallocated f1 frame from the stack, we allocate f2 frame where there was f1 frame. Consequently, where there was function f1 return address, now there is function f2 return address. Then we continue the execution and a power failure happens. When the device has enough energy, we restore the checkpoint but not the stack, and we resume from line 2. Note that the stack contains f2 stack frame, but we are inside the context of function f1. We execute a return instruction and thus we pop the return address from the stack, which is the one of function f2. As a consequence, the execution jumps to line 8, skipping the execution of line 7, which is the line that a continuous execution of the program would execute next. Note that in this example, the activation record anomaly overwrites f1 return address with a valid address. However, there are cases where the return address is overwritten with an invalid address, causing the program to crash. As we anticipated, activation record anomalies follow the same pattern of consumer-producer that we described before. In the previous example, the return from function f1 is the consumer, and the call to function f2 is the producer. We identify a similar case when we allocate the heap onto non-volatile memory. In this case, we have a memory map anomaly that may cause a corrupted heap state, which leads memory accesses to fail. We provide a more detailed analysis of this case inside the paper. As memory-based anomalies follow the same pattern, our consumer-producer generalization allows us to identify the minimum amount of information that we need to test intermittent executions. So, we emulate the program execution and we test a checkpoint before each consumer, as any checkpoint after a consumer prevents the intermittence anomaly to happen. Then, for each checkpoint, we need to simulate a power failure only after each producer, as those are the power failure that may cause an intermittence anomaly to happen. Finally, we use a lookup table to identify if an instruction accesses a value that a future operation produced during a previous power cycle. When we execute a producer that alters a non-volatile memory location, we save the clock cycle number when the memory location is modified. Note that the clock cycle number is restored with checkpoints. Then, when we execute a consumer, we check the lookup table. If the clock cycle number of the targeted memory location is higher than the current clock cycle number, we identify an intermittence anomaly. Note that this represents the key idea behind our technique, and we provide a more detailed description inside the paper. The previous analysis allows us to test intermittent executions and to evaluate the effects of intermittent anomalies. However, if you're only interested in locating where an anomaly may happen, we follow a different approach. We execute the program once and we retrieve its execution trace. The execution trace contains all the information that is usually not available at compile time, such as accessed addresses and executed branch paths. Then, we scan the execution trace to identify the consumer-producer pattern which we previously described. The presence of power failure can cause unexpected behaviors also when the program interacts with the environment. Let us consider the execution of this program which senses the environment temperature. We execute line 1, which sets T equal to 18, as the current environment temperature is 18 degrees Celsius. Then, we save a checkpoint and a power failure happens. Now, while the device is powered off, the environment temperature raises to 25 degrees Celsius. When the device has enough energy to restart the computation, we restore the checkpoint and we resume from line 3. Line 3 reads the environment temperature that T contains. However, this information does not reflect the current environment temperature. As a consequence, the if condition evaluates to false. Depending on the application requirements, this unexpected behavior may or may not cause a wrong result. Note that a similar case happens also when we alter the environment state using, for example, an actuator. To establish a correct behavior, we identify two input access models. A most recent access model, which indicates that we want to use the data that reflects only the current environment state, and a long-term access model, which indicates that we can use also the data that represents an old environment state. Then, to analyze access models, we proceed in a similar way to what we do for locating memory anomalies, and we provide the details of this analysis technique in the paper. To evaluate our techniques, we implement a tool which we call SHEPTIC, that stands for Simulator for Executing and Testing Intermittent Computations. SHEPTIC implements our analysis techniques and consists in a Python tool that emulates the execution of an intermediate representation of a program. This allows us to be architecture independent. You can find SHEPTIC source code and documentation at sheptic.netlab.it. For our evaluation, we use as baseline a layman approach, which is the same approach that we use for describing testing complexity, and which tests all the possible combinations of intermittent executions. Note that we choose this baseline because existing analysis techniques are not able to identify all intermittent anomalies, and they would provide incomplete information. As benchmarks, we use an heterogeneous set of benchmarks that are commonly used in this domain, and are CRC for data integrity, FFT for signal analysis, and IIS for data encryption. For each one of these benchmarks, we consider two different memory configurations. One, where only global variables are allocated onto non-volatile memory, and another one where also the stack is allocated onto non-volatile memory. Then we consider the MSP430FR5969 from Texas Instruments as target microcontroller unit. For each one of these benchmark configurations, we consider two different scenarios. In the first one, which we call a priori, checkpoints are not placed inside the program. Here we want to target a developer that needs to explore various memory configurations, so to identify the one that best suits its requirements. Instead, in the second scenario, which we call a posteriori, checkpoints are already placed using the strategy of mementos. Here, we want to target a developer that needs to perform a post-mortem analysis on an already deployed device that experienced some unexpected behavior. As we describe in the paper, SHEPTIC analysis is exhaustive, and what we are going to show next consists in an evaluation of our technique performance. So, to evaluate our technique performance, we measure the execution time of each analysis, the number of embedded code instructions that each analysis executes, and an output noise. This metric measures the amount of redundant information that an analysis identifies, and you can find more about this metric inside the paper. We report here the most interesting results for our memory techniques, and you can find a more detailed evaluation of all of our techniques inside the paper. We call SHEPTIC locate our analysis to locate where an intermittent anomaly happens, and SHEPTIC evaluate our analysis that evaluates the effect of intermittent anomalies. In the a priori scenario, we need to calculate layman performance by hand, as layman requires years to complete the analysis in such a settings. SHEPTIC locate is 10 order of magnitude faster than layman, and SHEPTIC takes seconds, whether instead layman would take years. As we can see from the instructions executed, this happens because SHEPTIC locate executes the program sequentially, whether instead layman needs to simulate all the combination of all the possible intermittent executions. In the a posteriori scenario, we have checkpoints placed inside the program, so we are able to execute layman analysis. Here, SHEPTIC locate is, on average, 3 orders of magnitude faster than layman. In the worst case, Shepti locate takes up to 54 seconds, while instead layman takes up to 20 hours to complete an analysis. Regarding Sheptic Evaluate is, on average, 5 times faster than layman, taking up 6 hours to complete an analysis. We can also see that these results are reflected on the number of instructions executed. In conclusion, the batteryless devices of the Internet of Things are characterized by frequent power failures which may cause unexpected behaviors that are recognized as intermittent anomalies. We analyze and classify intermittent anomalies in settings that current literature overlooks, both from a memory and environment perspective. Then, we developed and implemented a set of techniques to test intermittent executions in practical time and to verify the presence of intermittent anomalies. Finally, we implemented and evaluate Sheptic, demonstrating the potential and the performance of our techniques. So this ends my presentation. You can find Sheptic documentation and code at sheptic.nesslab.it. Thank you for your attention. I'm now ready to take your questions.